This video contains only one solution. This is the solution to problem number 48 from chapter 9. A couple of you had asked about this in email. In this problem, there's a pipe that needs to be driven into the ground. The pipe sticks out 35 centimeters above the ground, and I'm calling that quantity or that length lowercase h because within Mastering Physics, I looked at their solution and they used a lowercase h for this distance. In order to do that, they just take a very large weight. There's a machine up here called a pile driver, and it's a very simple principle. You just pick something really heavy high up in the air and drop it to let it smash the pipe in. So the pile driver's up here. I'll call this the weight, and it's got a mass m. And this picture is not to scale because this height, capital H, is considerably greater than lowercase h. This is only 35 centimeters. This is 150 centimeters, or 1.5 meters. And the question is asking you to find, during the time that this pipe is being driven into the ground, what's the average force that this weight exerts on the pipe, which is an interesting question. We know it has to be a large number because this thing is 250 kilograms. It's very heavy. We know it's going to push very hard on the pipe, but it would be difficult to answer this question without the work kinetic energy equation, which, as I will remind you, is F equals ma in integrated form. So again, they're asking for the force that the weight exerts on the pipe. Well, we can invoke Newton's third law and recognize that as the weight is driving the pipe into the ground while they're in contact with each other, the interaction between them consists of a pair of equal and opposite force vectors. The pipe pushes up on the weight just as hard as the weight pushes down on the pipe. So if we look at the dynamics of the weight, after all, the pipe is just chilling here. It's the one being driven in. The weight will be easier to analyze as far as its kinetic energy and the work being done on it. So let's look at the work done on the weight so that we can determine the force of the pipe on the weight. Once we have the force of the pipe on the weight, that's the same as the force of the weight on the pipe. So we'll have our answer. Okay, so what I've done is to break this process into two steps. I'm going to call T0 the time at which the weight is released. So it's dropped at T0. T1 is when it just begins to strike the pipe. And T2 will be the time at which the pipe is finished being driven into the ground. Now, when you use the work kinetic energy theorem, you don't really deal with time. You've already integrated F equals ma over distance. So it's really more about force being applied over distance, but certain events still happen at certain times. So it's useful to have these labels. Okay, so let's look at the work done on the weight for the first phase of the motion. I'm going to apply the work kinetic energy equation. Remember, this is the work done by all forces on your object. This is the change in kinetic energy of the object. And the reason why this is the work done by all forces is because this is the integrated left side of F equals ma. And the F in F equals ma is the sum of all forces. So you must calculate the work done by all forces. I've drawn a little free body diagram. And while this thing is falling, I only see a single force on it. That would be gravity. So we really only have to look at the work done by gravity. And the work done over that distance would be the work done between those two times, T0 and T1. So it's going to be the kinetic energy at time 1 minus the kinetic energy at time 0. That's the change in kinetic energy of the weight as it falls through that distance. Gravity's doing work. As a result, we get a change in kinetic energy. Now, I've crossed out the initial kinetic energy because presumably the weight is dropped from rest. And then calculating the work is very easy. This is a one-dimensional problem because the forces are all directed vertically and the motion is vertically. Also, the forces are all constant. Now, they're asking for the average force that the pipe exerts, or excuse me, that the weight exerts on the pipe. Realistically, when these two things collide, the force probably spikes in time. It probably starts out somewhat gradually and then spikes as they smash into each other, and then it dies back down to 0. But we're just going to pretend that the force between these two is constant as they interact. And that's what the book means by calculate the average force. We don't worry about those details about how the force might change in time. Okay, so since the force is gravity, mg, I just multiply that by the displacement, capital H, and I give it a plus sign because the displacement is down and the force is down. Those two vectors point in the same direction. The cosine of the angle between them, that would be the cosine of 0 degrees, that's just 1. So we give it a plus sign. And there's the work kinetic energy theorem. Here's the work done by gravity over this fall, and that's got to equal the change in the kinetic energy. Great, let's move on, because now we know what kind of energy we're talking about, and I may as well evaluate that off to the side here. Let's figure out just how much energy this thing has due to the work done on it by gravity. So if I take the 250 kilograms of the weight, I multiply by 9.8, and then I multiply by the height of 1.5 meters, I find that this thing has 3675 joules. But you know what? I don't even necessarily need that number. I'm going to solve it algebraically. I'm just writing it down because I'm curious. That's less than 4 kilojoules. So this thing has not even 1 calorie of energy, 1 food calorie. But it still sounds pretty destructive, right? If you drop it to 250 kilogram, that's over 500 pounds dropped through a distance of 1.5 meters. That would be something like 5 feet. So that's quite a bit of energy. Now we look at the work done on the weight over the distance where it's driving the pipe into the ground. Anytime you can identify the forces on an object and you know the distance through which those forces act, you can calculate the work. So I have to draw a different free body diagram. Gravity is still pulling down, but this time there's the additional force of the pipe pushing up on the weight. And I've drawn that vector longer. If I had drawn these vectors to scale, I think this would be way longer, because this force not only has to balance gravity, but it also has to accelerate the weight. So in a previous chapter, we would have looked at the kinematics. We would have talked about how forces produce acceleration, use the acceleration to calculate a change in velocity perhaps. But the nice thing about work and kinetic energy is that we skip all that. Again, the fundamental theorem of calculus, we've integrated F equals ma. We don't have to worry about the time derivative of velocity. We just look at the beginning and the end. Kinetic energy at the end, kinetic energy at the beginning. Okay, so the total work done now during the part where the weight drives the pipe in. Well, gravity is still pulling down in the same direction as the displacement. This time the displacement is lowercase h. So this quantity is the work done by gravity, but don't forget that the pipe is doing negative work on the weight, because as the weight falls down, the pipe is pushing up. That would be negative work. So I've taken the magnitude of the force that we're interested in times the displacement. This is just force times distance, and I've got the minus sign for negative work. And I set that equal to the kinetic energy at time 2 minus the kinetic energy at time 1, because I'm applying this equation for the dynamics between those two times, T1 and T2, when the pipe gets first struck by the weight and when the pipe is finished being driven into the ground. And of course I've crossed this out because once you finish driving the pipe in, it's not moving, it has no kinetic energy. Okay, let's move some stuff around here. I put this on the other side, I put K1 on this side, and then I just flip the whole thing. I get this equation. And we're almost at something that makes sense intuitively. So what I've done here is, instead of write K1, I substituted. K1 is numerically equal to mgh. Remember, this kinetic energy, the kinetic energy that the weight had before it struck the pipe, that came from the work done by gravity on the way down. So I just substituted here. And then let's divide by lowercase h. And I find this interesting expression. And this matches the solution that I saw in Mastering Physics. How hard does the pipe have to push up on the weight? Well, it's got to push up to balance the pipes, or the weights. I almost said the weight's weight. I'll put it this way. It has to balance the gravitational force on the weight, but it also has to, I'm going to put it this way, it has to remove the kinetic energy that the weight had. So this represents this is the energy that the weight had right before it struck the pipe. This force has to, in a manner of speaking, remove that energy. And it does that over a distance of lowercase h. So you just keep this in mind. Work, which is delta K, it's basically force times distance. So force would be work over distance, or you could say delta K over distance. So if you want to cancel all the, think of it this way, the gravity did work on the weight as it was falling, and now the pipe has to undo that work by doing negative work on the falling weight. So you just take the quantity of work that was done previously and divide it by the new distance. Or think of it as take the kinetic energy that it's got, and you're going to have to remove that over a distance d. That would tell you the necessary force. So again, this does come from F equals ma, but it's a different way of thinking about it. Instead of thinking about force producing acceleration, you can think about how much energy something has. Divide that by the distance over which you need to take away that energy, and that would give you the required force. And that's exactly what this equation says. So I don't even have to write mg capital H. I could just leave it as K1, right? These are the same. So I rewrote the equation down here. Keep in mind that as the pipe is being driven in, gravity is still doing work on the pipe. It's still doing positive work as the pipe descends into the ground. So the force of the pipe on the weight, it's got to cancel that work, so to speak, but it also has to take away the kinetic energy that it had from the first fall. So this equation, to me, the more I think about it, is really intuitive. I almost could have just written this down directly now that I've thought about this problem enough. I mean, it's good to go through things carefully and define your various times, write down which equation you're using, but hopefully you can look at this equation and see how it's kind of intuitive. The pipe on the weight, it's got to do negative work to cancel the work done by gravity as the pipe is descending, but it also has to cancel the work done by gravity during the first part of the fall. So you can plug in numbers, and I'll just do this on my calculator here. Let's start with this one. The kinetic energy it had, I already found that was 3675 joules. I'd have to divide by the 35 centimeters, that's 0.35. So this is in newtons. 10,000 newtons, that's something like 2,000 pounds. That's a tremendous force, considering that this thing was only dropped 1.5 meters, but that's because it's so heavy. So this is the force required to remove the kinetic energy, but then there's this additional force present because we have to just balance the weight of the weight. I keep saying that. The weight of the falling mass on its way down. So we would also have to add plus 250 kilograms times 9.8. And the total force would have to be, that sounds about like what Master in Physics said, 12.95 kilo newtons. So that's probably around 3,000 pounds. And the pipe pushes on the weight just as hard as the weight pushes back on the pipe. That's Newton's third law. And we've answered the question.